Yusuke is going to talk about Nola, later frequent state for verifying termination in arrays. Let's welcome the speaker.
Hello everyone, I'm Yusuke Matsushita from Kyoto University. Thank you all for coming here at the end of this conference. So now I'm really excited to talk about our work, Nola. To start with, reasoning about program termination in the presence of shared mutable state is really hard. For example, let's think of the program called Landinzot. Here, R is a shared mutable reference to a function. Clearly, no loop appears in the program, but actually this program loops infinitely. This doesn't terminate. Why? This is because the reference R is set to a function that dereferences R and calls its body. So, in other words, self-reference is created by shared mutable state. This is the source of evil. Our work, Nola, tackles this hard intersection of shared mutable state and termination. Before going technical, let me tell you the story behind the name Nola. It's actually an acronymic nickname for New Orleans, Louisiana, which is known as the birthplace of jazz. This explains why we use the logo of a trumpet for our work, Nola. Also, in the city, there was Popol 2020, the first and last international conference that I attended before the pandemic. I miss the amazing time I had in the city. So now I'll give you a high-level overview of our work, Nola. Notably, the name Nola also stands for the phrase, no later. What does that mean? Well, Nola can help you finish your work soon, no later, maybe. Well, more technically, there's a feature called the later modality, denoted by the right-pointing triangle. It's a central but notorious feature of Iris, the well-known separation logic framework that you might have heard of. Remarkably, our work Nola proposes a novel way to remove this later modality, which gives you the power to prove more things in Iris. Let me put it more precisely. The later modality in Iris originated from a strong mechanism for reasoning about shared mutable state, namely invariance and borrows. Iris used the later modality to make the logic sound in the presence of these features. But the modality is actually a fundamental obstacle to verification, especially of termination or liveness properties. Nola enables you to remove the later modality while retaining the soundness, and empowers you to prove challenging properties like termination. Of course, our work is fully mechanized in Roc, and also as a library of Iris compatible with existing developments of Iris. So you can start using it now. Now, let's overview the motivation in more detail. Invariant, denoted by box P, so the box is part of the notation, and this roughly means that the situation described by the separation logic assertion P always holds. Remarkably, invariants are shareable, so they can be used to model the shared mutable state, especially the shared mutable reference type. Remarkably, this model of references can easily be nested simply because the invariant itself is a first-class separation logic or Iris proposition. We do need the invariant since we are in the world of separation logic, where an assertion like the points to token is not shareable, as it can be broken by state mutation. But there is a problem about the invariant. The naive invariant that you might expect is actually unsound. Naively, we expect this rule where P is preserved in the execution. But it's unsound. We cannot directly throw any SL assertion P in general. More concretely, there are paradoxes which are related to Landinzot at a high level, which I showed you at the beginning. the non-existing fix used by the current iris is to weaken the shared content by what is called the later modality. So they update the access rule of the invariant into this. In other words, this version of invariant asserts that the situation later P instead of just P always holds. To clarify this fact, in this talk, we write a gray later modality inside the box. The later modality weakens the proposition strictly, and it's not even transitive. This nature of the later modality avoids the paradoxes and brings the soundness, but it makes the invariant weaker than we naturally expect. In particular, there is a remaining challenge in termination and liveness verification due to the later modality from the invariant. More concretely, we cannot reason about the reference of shared mutable references. Recall that shared mutable references can be encoded using invariants, but now the invariant is weakened by the later modality. Due to this, when you dereference the reference, you come across the later modality, which actually blocks accessing the content of the reference. We note that this wasn't the case for the partial Hoare triple, which does not have the termination guarantee. Technically, it can internally strip off the later modality using a technique called step indexing. Unfortunately, it's well known that step indexing does not work well in termination and liveness verification. This is admitted by the paper of Similaris, a logic that targeted termination preservation. Similaris gave up the invariant due to this very reason. So, can we solve this frustrating situation? Nola is here to solve this. Its key idea is so simple. Use syntax. Well, more precisely, syntax for separation logic assertions to share. So technically, syntax gives you better control of what can be shared in the invariant or such features, and to avoid paradoxes and achieve soundness. And this gives you better, finer control than the later modality. Long story short, the new invariant access rule in Nola is this. Crucially, the invariant uses syntactic separation logic formulas to describe what can be stored. Also, syntactic formulas are embodied into iris propositions using the semantics function that is separately constructed. Remarkably, proofs themselves can be written semantically with usual iris propositions in iris. So Nola uses syntax only for formulas, not proofs. You can use Nola just as a library of iris in this sense. So I'll show how Nola's use of syntax clears away the later modality. First, we just build the syntax for separation logic formulas and also define its semantics. For example, we can build syntax for formulas like this. Crucially, it includes the invariant. You can just define the semantics by structural induction like this. And importantly, this just works for the invariant. Now things are just later free. You can remodel the shared mutable reference type as a syntactic formula like this if you use Nola. And this allows you to enjoy the later free access and make the dereference just work. As a verification example, we show infinite shared mutable lists which even contain cyclic references. If we use Nola, no later modality remains in the tail of the list, unlike iris. So we just enjoy the later free access. Thanks to this, we can verify termination of many things, including iteration over a list like this. And the proof just goes very naturally by like metalogic induction and or like that. So you might wonder, why is Nola sound? How is it expressive? Well-definedness of the semantics is actually the key to soundness. In particular, Nola doesn't suffer from the paradoxes of London's knot. If you were to try to directly store the total whole triple into formulas, then you would have the ill-formed self-reference in the definition of the semantics. So this is actually rejected as a definition. Still, Nola allows flexible construction for extra expressivity. For example, we can support advanced constructs like whole triples under the later modality subsuming the existing approach. Another way to support advanced constructs is stratification, where we have layers of separation logic formulas. To experts, I would like to advertise the power of SL formulas a bit more. First, we can actually store any semantics SL propositions under the later modality. So Nola precisely subsumes the existing later weakened approach. Also, the set of SL formulas can even be extensible. This can be done by parameterizing the proof over the constructors to be used. This pretty much resembles how I plus sigma parameter works. To experts, I would also like to briefly mention that Nola's model for the invariant just generalized Iris's model, as shown here. This gives a different view of how Nola works. Remarkably, Nola can also model Rust-style borrows in the style of the lifetime logic by the well-known work Rust Belt, but in the later free manner. In Rust, there is a feature called borrow, which is a sort of mutable state shared between the borrower and the lender. Long story short, Nola can reason about Rust's borrow in the separation logic Iris like this. More technically, Nola provides a set of proof rules like this. It's more advanced than the invariant, but the key idea of using SL formulas and its semantics is just the same. As a case study of Nola, we built a prototype version of Rust Hold, a semantic foundation for verifying termination or total correctness for verifying termination. Or total correctness of Rust programs. For example, it can verify the total correctness of a Rust program that iterates over a list like this. Technically, it refines Rust home belt, an extension of Rust belt for functional correctness with Nola's invariance and borrows. Notably, although syntax is used for semantic SL formulas for Nola, we can build semantic typing or logical relation that enjoys extensibility. So this has a semantic model like this. I would also like to briefly mention recent work Lilo, which applied Nola-style invariance to verify liveness under fair scheduling. Technically, it uses stratification to support higher order features. For example, Lilo can verify fair termination preservation like this. To experts, I would like to briefly tell you about our new finding, magic derivability, named so because it is so magical that I still don't fully understand how it works. So at the high level, it can be used for proving subtyping on shared mutable references semantically. Our magic derivability magically solves this beautifully by something roughly like a fixed point. This is quite cool stuff, so please read our paper for the details. So this is a summary of our work, Nola. That's all for my talk. Thank you.
Any questions? Yeah.
Hi, I'm Zhong Shao from Yale University. Actually, 20 years ago, before people started to settle on using step indexing, there's actually lots of work on try to find a syntactic approach to reason about a high-order feature like first-class code pointer, embedded reference. So there's this line of work my group did on XCAP, which actually, we use exactly the same syntax-based approach, and it was actually being used by, Adam Chipala's Bedrock and so on, around 15 years ago. So I wonder whether you are aware of that work, and if yes, what's the relationship?
Yeah, thank you for the pointer. So yeah, we are aware of that work actually, but we feel that the mechanism feature attained by that syntax approach of XCAP is kind of different from iris style invariance. So yeah, it's kind of different from shared mutable state in this sense, we would argue. So that's one difference. And also another difference is we pursue more extensibility or generality in this work. So yeah, we are aware that there's so many work studies to compare with Nola, but we would say that Nola is kind of one work that's kind of proposes really general approach of combining the iris world and the syntactic approach.
Okay, we can go offline, but I think it's clearly related, and I'm disappointed that your paper does not even cite our work as related.
Yeah, sorry.
Okay.
Hi, Simon Spice from Jane Street. Could you go back to slide 11, I think it was?
11, okay.
Yes, yeah, the example with the total Hort triple. Yes. If you were to put a total Hort triple into the invariant, you wouldn't be able to get rid of the later that now appears here, right?
You mean this model?
Yeah.
So yeah, so that's actually the problem. So if it were just partial Hort triple, then this definitely works by step indexing. And yeah, for total Hort triple, maybe we currently don't have a technique, but I kind of thinking of solving that.
Right. Yep.
Yeah.
Thanks.
Further questions, comments?
Nick Swami from Microsoft Research. I'm just curious, in a way, by using this piece of syntax, you're kind of delimiting a universe of syntactically denotable iprops.
Mm-hmm.
Is this powerful? Can you always do this? I mean, it seems like the cardinality of this thing would be too small in some cases.
You mean too small for some specific applications of verification?
Exactly.
I see. So yeah, that's a really good question, and so maybe short answer is we don't fully know the expressivity yet, and so. But one thing I can say is that so we can basically subsume the original iris approach using the later modality. So by combining that technique with the syntax, then probably we can verify more things, hopefully.
We tried this at some point in Pulse, trying to use syntax to break this the circularity, and examples like task pools, where a task refers to the task pool itself. I think we were not able to encode it via syntax. I wonder if your system can.
Okay, yeah.
We can talk more.
Yeah, let's talk offline. Yeah, that seems interesting. Thank you.
Probably it concludes the last session, and I'm not in a position to say that, but you are now formally dismissed.
I can say that.
Okay. Thank you all for coming to Korea.
Thank you.